So what is the Higgs, or the Higgs boson? What is the Higgs field? It's difficult to visualize. So many people resort to metaphor. It's kind of been described as a kind of cosmic molasses. It has been described as dragging on particles as they move through it. But we'll use a field of snow. A skier meets little resistance and glides easily across a snowfield. A woman shuffles by on snowshoes and is slowed by the snow. And a man in heavy boots plods along, slowed at every step, while a bird flies over untouched. The Higgs field is like our field of snow. But instead of countless snowflakes, the field is made up of Higgs bosons. Particles that interact with the Higgs field have mass. Like the skier, electrons barely interact with the field. They have very little mass. Like the snowshoer, the quarks that make up protons and neutrons interact more strongly with the field. They have a bit more mass. The W and the Z bosons plod through the Higgs field like people in heavy boots. They have thousands of times more mass. Photons and gluons don't interact with the field at all. They are massless. 50 years ago, physicists had no idea why some particles had mass and other particles did not. So they thought up the Higgs and have been searching for it ever since. It's like an elusive missing snowflake in our theory of falling snow. In search of the Higgs. Imagine never having seen a snowflake. Now prove one exists by probing the slush and mist of melting snow. You can't see the Higgs boson, and no sensor can pick it out of the form or pick it out from the Higgs field that it forms. For 50 years, physicists have been building larger and more powerful accelerators to vaporize particles and sift through the debris. In the tunnels of CERN, protons are sped along track to within a breath of the speed of light, then smashed together in a violent explosion. The protons annihilate each other, releasing a burst of energy. But Einstein tells us that mass is energy, where E equals mc squared. The energy is equal to the mass times the speed of light squared. And physics tells us that energy can't be destroyed. An array of new particles pours from the fireball after the collision. And energy spun back into tiny specks of mass. A machine surrounds the tracks and tracks the debris, bending charged particles as they plow through the layers of sensors. Repeat this 1,000,000 times, then tens of millions, before a second has passed. And keep going because you're looking for something very rare. Once every few billion impacts, a Higgs boson pops into existence. The moment can't be sensed directly, so it triggers no celebration, no champagne. But the Higgs is unstable and splits into a cascade of particles. After trillions of collisions, these fragments of the Higgs might accumulate statistically to form a bump on a chart. With more data, the bump grows past uncertainty and clears a statistical hurdle. A discovery has been made. A trace of the Higgs boson.